Okay, here we have our second part. Which we're going to continue with the first pattern of deduction, a rule of inference. Now, I've given them names. Do they have Latin names, these particular patterns? But the Latin names aren't particularly informative. So, and you might see them in a critical thinking course. And I do mention in the text, I think, is a footnote down here, but that's not really important. Okay, so I'm going to call this a firm premise because it sort of describes what's going on in the rule of inference. Okay, so the premise, there's two premises. Premise one is that P, this is given any propositions. Any propositions P and Q. Our first premise is that P implies Q. Our second premise is just that P is true. Okay, well, the first premise intuitively says that the truth of P guarantees the truth of Q. Well, the second premise is, well, we know P is true, therefore it's intuitive that we should conclude that Q is true. So these three dots here are a simple way of saying therefore, symbolic way of saying therefore. They mark the conclusion. Okay, so here's an example in the text. Let's say that P represents or denotes, which is represents or names the proposition it is snowing, which is a snow day is appropriate, but in fact, it's maybe not so appropriate because although it's a snow day and it should be snowing, it's rather difficult to shovel any snow because I look outside, I don't see any snow yet. And but let's say that so P might be true or might not be true where you are. And Q denotes it as cold. Right now, that's definitely true. But our first premise then is P implies Q is if it is snowing, then it is cold. Our second premise is it is snowing. Well, the claim is that if both of these are true, we know it's cold. If it's snowing, it's cold. It's snowing, therefore it's cold. Now, it doesn't if now right now it might be that the second premise might not be true, so that doesn't affect whether the argument is valid, whether the pattern of inference is valid or not. It might not be a sound argument at this particular time, but it's certainly valid because the truth of the premises guarantees the truth of the conclusion. What that means is a valid rule of inference corresponds to an inference. It corresponds to the fact that P implies Q and P has to imply Q. This has to be a tautology, a true statement all the time. Can't depend on whether P and Q are true. Now, so showing that this is a valid rule of inference means showing that this is valid. Now, there's several ways to show this. One is via truth tables. Here's this inference. P implies Q and P implies Q. We want to show it's a tautology. Well, here's the truth table that shows that this is true because we use the definition of implies with P and Q here to get the truth values. The only way this can be false is if P is true and Q is false. But then we look at the and. That's the and of all the premises. And we can see now that then the only time that these are both true is in the first row because we need them. We need not Q, but we need P implies Q and P to be true. That's here. Because for the other ones, one of them, here P implies Q, here P are false. So the and of both of them is false. Now, the only rows that are relevant to whether the rule of inference is true is the first row, because that's the only row in which all the premises are true. Now, if this was false, it would be a valid, if any row in which all the premises are true, but the conclusion is false, then the premises wouldn't guarantee the truth of the conclusion, and it wouldn't be a valid rule of inference. In this case, the only time in which the premises are true has a true conclusion. Because you see, you have true, true, and Q is true. So therefore, this is a valid rule of inference. Now, we can also show this with our logical equivalences, which takes a little work. And since that's something we do, I may as well show you how that works here, although it may be a little bit tedious. Um, Gives you an example of how to convert a statement using logical equivalences. Now, to do this, we need to have handy the logical equivalences, which are handy in this form here. We have this, let me make this so it's a little more accessible. We can get both pages on visible. Okay, these are the core logical equivalences. And the sheet that you have on the resources page on Piazza. And there's one, you notice that there's only one rule that has these arrows, implications, and that's this one. So the only way we can start doing anything is by using this rule, in which if X implies Y, that's logically equivalent to not X or Y. So we don't have to apply them everywhere. Let's apply them first just to this statement here. What I'm going to say is this implication is logically equivalent to, I'm going to apply this pattern so that P is X, Q is Y, and this is going to be not P or Q, right? This has replaced this here. And that's the whole point of a logical equivalence, is that if I make this substitution, it does not change the truth value of the proposition that results. So that means that if the first one is true, the second one is true. And the first one is false, the second one is false. Okay, well, let's continue now. We can see what the strategy is, that you see a P here and a not P here. If we can bring those close to each other, then they might annihilate each other, because we will either get P and not P, or P or not P, and replace it with a true T or F, and that simplifies things. So let's see if we can't get this P next to this not P. Now, one thing is, we could distribute this in, but it might be nicer to, and we could do that. Let's make it look exactly like, well, this is P or not P. So let's first say, well, we know that we can reverse the order of an and. That's the commutative principle here. X and Y is the same as Y and X. So this is logically equivalent to, I'm going to reverse the order here, P and not P or Q implies Q. So the only thing I've done is I've reversed the order of these two propositions. Now, this is an and, this is an or. So to get the P and the not P together, we can use the distributive principle, because and distributes over or. So we can apply this distributive principle part A here, and the way it'll work is this. P and not P, that's the first one. This comes in and latches there, or P and Q. The P and distributed into this and this implies Q. Now we've got these next to each other, and if we look down at the logical equivalence simplification C here, X and not X, that's P and not P, we can replace that with F, because this says it's never the case that P and not P can be true. So we can substitute this for false, or P and Q implies Q. Now, the only way an or can be true is if one of these are true. So this is always false. So this whole thing is going to be only true if P and Q is true. So that's this simplification here. It's the opposite order, but since we can reverse the order, this is also that F and X is false. This is or though, so we're not in A, we're in E. X or F is X. So we can replace this with P, and Q implies Q. Now, now it's time to use the implication identity down here to get rid of this other implication. So we can say that's logical equivalent to the not of the first proposition. You have to be careful with your parentheses here to match up the pattern, because X here represents P and Q. So it's the not of P and Q, then you have an or, and Y is Q. Okay, so then we want to bring in this not to sort of not have these parentheses here, so we can deal with these individually, because we can see if we can get this not on the Q, we might be able to get the Q and the not Q here and this together. So let's use the De Morgan principle here to bring in the not, and that is going to change the and to an or, like that. And then now we see this is an or and an or, so we can use the associative principle. When the logical operators are the same, we can change the parentheses. So this is logically equivalent to not P or not Q or Q. Now, so these are then we've gotten the not Q and Q next to each other with an or, and we can look down at the simplification here, and we've got not Q or Q. Well, this is just the opposite order, but we know it's commutative, that we can switch the order. So we know this is going to be true. So this is going to be logically equivalent to not P or true. And any statement or true is going to be true, because since this is true, the or is true. So this is logically equivalent to true. That means that through this series of logical equivalences, each one's logically equivalent to the next. There's a long sequence of operations using this stuff, but then we know that P implies Q and P implies that Q is true, is a tautology. So if we know that, if we start from P and P implies Q, our move can be Q. That justifies saying, making the move from P implies Q and P to Q. So that's what that's what we say here. We say if it is snowing, it is cold, it is snowing. We can make a new statement that we know is going to be logically implied by these two. It is cold. Okay, so these are two different ways with truth tables, and this calculation is also presented in the text in a more compact form. In fact, in two different ways. So there's a lot of logical equivalences there. And you can see that the point is it's much easier to just use this principle than it is to justify it. But once it's justified, then we don't have to worry about how it's justified with the truth tables or the logical equivalences. There are logical foundation, but then we make an argument or a proof, then we can just use a firm premise without worrying about the details of we can treat it as a known result. Okay, so that is our first rule of inference. And now we're just going to go become familiar with the rest of them. We're not going to go through. In the text, it goes through and shows you the truth table and stuff for these other ones, or the logical equivalence derivation of these patterns of inference. But let's just go on now that we've justified our first one, a firm premise. And here, so our first one was a firm premise in which premise one was P implies Q, and premise two was just P, and our conclusion was Q. Okay. Well, let's continue with deny conclusion.